Okay, so in this problem we have some mock data for an experiment where we're sort of building a catapult and using a counterweight to launch a ball distance x. And so we're seeing sort of how the mass of that counterweight that falls changes the distance x that the launched object travels. So the first thing we have is we have this graph where the data points are plotted, everything's all nicely labeled for you, and your job is to just sketch a best fit curve for these data points. And it's important to note that this just says best fit curve. It doesn't specify that it's linear, quadratic, or anything like that. It just says whatever curve fits the data best. And so that means it's up to you to try to figure out what shape you think it is. And some of that we're going to address in more detail when we get to parts B and C. But for now, we just kind of see what shape sort of this looks like. And when I look at this, I see kind of a square rootish type shape, right? It increases a lot at first, and then it kind of levels off. So I'm going to make kind of that sort of curve, right? Kind of like that. Now, you shouldn't play connect the dots, right? The red is a good one. If I did something like this, I would lose points for that. That is not a curve. That's, right, just kind of connecting dots together. So don't do that. Do a smooth curve, trying to get as close to many of the points as you can. And so now we've used our best fit curve, and we need to figure out the distance that would be traveled if we put 250 kilograms in the counterweight. So 250 kilograms is roughly there or so. Actually, I'm going to use a different color. Is roughly there or so. And so we just trace it up. Yeah, actually I'm going to move that a little bit. It's a little bit farther out, more like there. So we trace that up, and we get there, and we trace it over, and it looks like we predict, since each of those spacings on the y-axis is 10, we predict, about 27 or so? Yeah, about 27 or so meters. Now, if you drew a different curve, right, like this orange one, maybe you really like that point that I kind of left out as an outlier. So maybe you did something that looks more like that. So then we would trace a slightly different spot. Right, we would trace up like this, and then kind of over like that, and we might get more like 30-ish meters. Exactly what you get, all of the key is it has to be dependent on your graph, right? That's the only key. Whatever your graph says, do, and this is kind of the process. So I'd say something between 27 and 33 meters. My graph, the orange line, I'm going to write just about 27 to 33 meters is a good estimate, but it should be just whatever graph your graph shows. Okay, so that's the graph part. Actual calculations, try to figure out what we would predict it to be, right? All we've done so far is we've sort of said our data says it should be that. But if we were actually to predict from sort of basic physics principles, what do we think it's going to be? And so to do that, we're going to develop this model, right? By ignoring the mass of some things and talking about the mass of others, we're going to try to explain, in terms of energy, essentially, what's going on. So the first thing, in B part 1, how many seconds after leaving the cup does the projectile hit the ground? Well, that's a kinematics question, right? Once it leaves the cup, it's a kinematics question, and it only depends on the vertical height that it falls, right? We are told that we have like this lever arm, and then like the base part, and this is 12 meters, and this is 3 meters. So it has to fall a total of 15 meters, right? It comes out like that. We don't care about the horizontal part here. All we care about is the time, and that's only dependent on the vertical part, 15 meters every single time. So our kinematics equation is going to be this. Consistency. Okay, and we're launched horizontally, so this term is 0. Our final height is 0. Our initial height is the 15 meters. That equals. And acceleration is gravity, right? So we're going to get 15 times 2 all over g equals t squared, or t equals square root of 15 times times 2 over 9.8, which is going to be about 1.75 seconds. And you could make that 1.8. That would be an acceptable sig fig answer. I think 2 sig figs is reasonable in this problem as well. So that's part one. That's how long it takes to hit the ground. That doesn't matter at all of anything other than the sort of height of that catapult arm. Part B. Actually, I'm going to go to a different page for this one because this one will take. So part B, we need to relate the gravitational potential energy of the whole system. Well, actually, sorry. We just need to write what the gravitational potential is in figure 1. So figure 1 is when it's sitting sort of horizontal, ready to launch. That's the energy that we're going to be converting into kinetic. Right? So gravitational potential energy of the system relative to the ground. So this is going to be, I'm just going to put this in quotes, mgh, right? That's UG. And so all I have to do is figure out what mass is involved. Well, there's 2 things we're keeping track of the mass of. The mass of the weight we're launching and the mass of the counterweight, right? So we have 2 potential energy terms. So this is m, let's see, c for counterweight, gh, plus m projectile, gh, right? And we can look at the picture and we can see that they're all 3 meters above the ground. So GH is the same, so I'll factor that out, 9.8 times 3, and we just have to add the masses, right? So the counterweight is m, and in the first part of the problem, we're told the projectile is 10 kilograms, right? So all I have to do is multiply the 3 and 9.8, so this is going to be 29.4 m plus 294, right? That's an expression that describes how much gravitational potential energy we have in figure 1, right? Depending on how much mass we put in the counterweight bucket. And so now we can put all this together and figure out the velocity that the projectile leaves the cup at. Since we've done an energy part in part 2, that should kind of clue you in that we're going to be doing something with conservation of energy, right? We're assuming there's no friction in that sort of rotation part, and we're just going to conserve energy. So E initial equals E final. This is E initial, right? It's not moving initially. But E final is made up of a couple different parts. So looking at this, the final energy is what's pictured in figure 2. So we have the kinetic energy of the projectile, right? That contains what we want to find. But the projectile is also some height above the ground, specifically 15 meters. So we have potential energy for that as well. And then finally, in a very easy to forget term, the counterweight, the distance between the pivot and the counterweight is 2 meters, but the distance between the pivot and the ground is 3 meters. So the counterweight does not reach the ground. So there is, I'm going to call this HP. There is a capital M for the counterweight, G, and then HC for counterweight left over as well. Right? The counterweight does not reach the ground, so it still has some gravitational potential energy remaining. So now we can clean up this side a little bit. And actually, we're going to have to put it all together. I'm not going to do this a whole lot. So, write these things and set them equal, and we're going to solve for V. So, the mass of the projectile is 10 kilograms, so that's 5 V squared. 10 times 9.8 times 15, that's mpg times the height of the projectile. And that is 1470, or no, that's not right, wrong number. Oops. No, I was right, it is 1470. All right, so that's the projectile's potential energy after. Then if you add in, so I have to start a new line because I ran out of space. We have to add in capital M, And then G and HC, oops, and that is just going to be 9.8 capital M. Right, because G is 9.8 and the height remaining is 1 meter above the ground. So we need to rearrange this to solve for V. So we can combine the terms that I'm going to put underlined in red. Right, 29.4 minus 9.8 M is going to be 19.6 M. We can also combine the terms here and here. So that is going to be 294 minus 1470, and that is minus 1176. That equals 5v squared. Right? And here's where I realize I forgot another term, right? We haven't come to rest instantly yet, so there's also a kinetic term involving the counterweight, right? As it reaches that lowest point, it's still instantly moving, just like the projectile is instantly moving. So we have to include its kinetic energy too, which I'd forgotten. And these velocities are going to be the same. They're not going to be the same, sorry, hang on. And so these speeds are not going to be the same because they're different distances from the pivot. So we need to figure out how to relate VC to VP, which I'm going to do in this little space over here. Right, so that's VP, and this is going to be VC. This is 12, and this is 2. So since the projectile is 6 times farther, it has to be moving 6 times faster. Right, that's the rigid body rotation statement. The radius is 6 times bigger, so it has to move 6 times faster. So VC equals VP over 6. So now we can substitute that in. So we get a 1/2. Actually, sorry, not 1/2, because we're gonna combine that 1/2 with the 6. So 6 squared is 36, and 1/2 of that is, so 1 over 72 mVp squared. And so now we can actually keep going where we left off, right? So there's a plus 1 over 72 mVp squared. So we have everything with the velocity on one side and everything without the velocity on the other. So we need to factor out 5 plus m over 72 Vp squared. Divide by that thing in parentheses. We're going to get Vp squared is 19.6 m minus 1176 all over 5 plus m over 72. So I'm just going to take the square root without rewriting it, like so. Right. Let's do that. Right, and so that's our final answer. It's really, really ugly, right? Yeah. Okay. That's our final answer, though. The velocity of the projectile in terms of the counterweight bucket mass. Right? And the key is energy conservation. That's where it all comes from. We did the initial energy pretty straightforwardly. The final energy is a little bit tricky. You have to remember both kinetic and both potential energies. But it's doable. Okay. So now we're on to part C, where we have to put all of this together, which combines the results from before. So we have a statement in the original problem that x equals vt, right? V projectile times t. We calculated v projectile, right? Square root of 19.6 m minus 1176 all over 5 plus m over 72, and then t, which we calculated earlier as 1.75 seconds, right? That one doesn't depend on the counterweight mass at all, so it's a little bit simpler. Right, and that's all part C is putting the two things together and recognizing sort of where they go. Right, so this is C part 1. And C part 2 is now make a prediction So plug in x as a function of the mass 300 kilograms, right? So all I have to do is plug in 300 in here and there and see what you get. And if you do that very carefully, right, your calculator can be a tool, but if you don't forget all your remember all your parentheses, make a mistake, you can mess it up. So you have to be careful, but if you do it carefully, you're going to get about 39.7 meters, or maybe 40 meters. So that's what we get. That's the result we get. That's not what we predicted, right? And so now we have to compare. So we notice that x from the data is less than x from the theory. And the question is, why? And there's a couple different reasons why. The first is, look at the assumptions that we made in the problem. We said that the mass of the rotating arm, the mass of the cup our projectile sits in, and the mass of the counterweight bucket that those counterweight masses are sitting in is ignorable. That may not be true. If that mass goes up, that's going to change the, like these values here. And so we can get a smaller mass from that. Another thing, what about air resistance, right? If this ball is relatively sort of large, you can have a noticeable amount of air resistance. That's going to decrease the distance it travels. We didn't calculate air resistance at all in this. Another thing, maybe there's friction on the pivot point, right? A friction force would cause the arm to rotate a little bit more slowly, and so we'd be launching it a little bit more slowly, and so then we wouldn't travel quite as far either, right? So any of those possible ones, the key is just to make sure to discuss it clearly and show how it makes this, right, not just that it's different, but that it's specifically that we measure something that's less than that number. So something that would make it go more slowly or less distance.